Welcome back to the Dr. Liu VCE Physics channel. In this video, we'll review the 2025 NHT Physics exam, focusing on questions related to electromagnetic induction. My explanations may not be perfect, so if any teachers, parents, or students notice any errors, please feel free to offer your feedback. When a rectangular coil of wire is rotated in a uniform magnetic field, B, both the magnetic flux through the coil and the induced voltage vary. The diagram below shows the coil of wire when it is parallel to the magnetic field, diagram 1, and when it is perpendicular to the magnetic field, diagram 2. Maximum flux, 0 EMF. When the coil is perpendicular to the magnetic field, the magnetic flux is at its maximum. However, the instantaneous rate of change of flux is 0, resulting in 0 induced voltage. 0 flux, maximum EMF. When the coil is parallel to the magnetic field, the magnetic flux is 0. At this point, the instantaneous rate of change of flux is at its maximum, resulting in maximum induced voltage. A single square loop of wire of area moves at constant speed from outside left, into, through, and out of a magnetic field, as shown in Figure 12a. Assume that the magnetic field outside the poles of the magnet is 0. The area between the poles of a strong permanent neodymium magnet has a constant uniform magnetic field of magnitude 1.4 T. Figure 12b shows the view from above. The induced electromotive force, EMF, is generated only when the magnetic flux through the coil is changing, as defined by Faraday's law. Outside the magnet, magnetic flux is 0 and unchanging, so EMF is 0. Entering the field at a constant speed, the flux increases constantly, is a positive constant, inducing a constant negative EMF. Inside the uniform field, the magnetic flux is constant, at its maximum value, meaning the rate of change of flux is 0, and therefore the induced EMF is also 0. Exiting the field, phase 4, at a constant speed, the magnetic flux decreases constantly, is a negative constant, inducing a constant positive EMF. The 1.5 s time interval measures the duration required for the loop to completely exit the magnetic field. During this delta t, the induced electromotive force, EMF, is constant and is calculated by Faraday's law of induction. As the loop moves out of the magnetic field, the downward magnetic flux decreases. By Lenz's law, the induced current produces an opposing, increasing downward flux, which requires a clockwise current in the loop, by the right-hand grip rule. This section is worth 10 marks and contributes to 8.3% of the total score, 120. Multiple choice question, 1 mark, question 9, examines the relationship between magnetic flux, B, and induced electromotive force, EMF, for a loop rotating in a uniform magnetic field. When the loop is perpendicular to the magnetic field, the magnetic flux is maximum, and the EMF is 0. When the loop is parallel to the magnetic field, magnetic flux is 0, and EMF is maximum. Short answer questions, 9 marks, question 10a and 10b, examines a loop moving in and out of a uniform magnetic field at constant speed. Outside the magnetic field, magnetic flux and EMF are 0. During entry or exit, the rate of change of magnetic flux is constant, resulting in a constant EMF. Inside the magnetic field, magnetic flux is constant, resulting in 0 EMF. Question 10c requires the calculation of the EMF during the loop's exit phase using Faraday's question 10d, requires the identification of the direction of the induced current using Lenz's law. Should you require assistance, Please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE Physics, Chemistry, and Biology channels.